So far, we've only rotated things, regions bounded underneath one particular curve. We're now going to think about revolving regions bounded between two curves. So this is analogous to us having first used the integral to compute the area underneath a curve, and then using the integral to compute the area bounded between two curves. Here is a three-dimensional analog to the exact same problem. So let's take a look at our first setup here. We are asked to rotate the region bounded between y equals x and y equals x squared all around the x-axis. As always, let's first sketch what this looks like. So I have my two axes, x and y. My first curve is y equals x. Here it is. Let's label it. And my second one is y equals x squared. So it's a parabola, y equals x squared. It will be essential to actually find this point of intersection. So in order to do that, you're going to set these two to be the same, and you're going to notice that this point of intersection occurs when x is equal to 1. So I might as well just put it down here, 1. Okay, now I have to rotate this whole thing around the x-axis. So rotating both curves, it's literally the same as rotating just one of them. And what you're thinking about is what happens when you rotate the region between them across the entire x-axis, okay? So again, here you're really going to have to switch on your three-dimensional thinking. But the thing that might help with it first is just to draw the exact opposite picture. So there we go. And the parabola, this is going to be a little challenging. There we go. Something like this. Oh, this is not half bad. Okay, so this is where my region of rotation is going to end up. And of course, this whole thing is three-dimensional. So I really have this thing. But again, remember, I'm only rotating the actual region between it, which means that I'm getting this like sideways looking ball, right? There's nothing in the middle here. It's just these pieces that got rotated and got connected. So it's hollow in the center, and this is something that I'm really going to actually take care of. Let's draw in a typical disk. Okay, so what I have here is if I'm rotating y equals x, I'm going to have a disk that looks like this. On the other hand, when rotating y equals x squared, I'm going to have a disk that looks something like that. Right? Now, just because I have a lot of things going on my graph, I'm going to draw in those disks separately. So this guy is the one that's generated by y equals x, and my inner disk is going to be generated by y equals x squared. So what I get in the end, again, because rotating just this region around will produce a hollow bowl, what I really get is not a disk, but rather a washer. What I'm interested in is this area of it, not the center. I have taken the center out. The thing that I like to think about as an analog for these, it's kind of like donuts, right? So if you rotate just y equals x, you're gonna get all of this inside of it. But you don't want the whole thing. You want the middle portion out. So this little disk in the middle that you're gonna take out, it's kind of like taking out the timbit, right? This is what's going to create the hole in the middle. These are the holes you have to take out of your donuts in order for them to be cooked properly, essentially, right? So sometimes some books call this the washer method. This really doesn't need a new name. It's just two different disks, right? So what I have to do in order to calculate this volume is I have to calculate the volume created by the big disk and then subtract the volume created by the little disk. So let's write this out. Using the disk method, the volume now corresponds to the integral of the, remember the formula was pi r squared h, so pi r squared, but first I'm going to take the outer radius for my bigger disk minus pi r squared for the inner radius, or my little timbit that I'm actually going to subtract out. Okay, now we haven't specified the variable with respect to which we're rotating, or the limits of integration. So let's think about that. Look at my disks here. This is the thickness of the volume that I'm rotating. And so this is easy to get confused with, which is why when you're deciding what variable you're going to use, it's probably best to think about it one disk at a time. When I was drawing my purple disk, right, its thickness was present here, right? And when I was drawing in my red one, its thickness was present on it this way. Okay, so the thickness of each disk, and I have to actually include them here separately, were both along the x-axis, which is again consistent with the fact that using the disk method, if you're rotating around the x-axis, your integral is going to be in terms of x. So my variable here is going to be x, and then we need to decide the limits of integration, and I have to go in terms of x from here to here. So that would be from 0 to 1. Okay, and now all I have to do is actually plug in the corresponding functions. This is why this is the step that makes it clear that it's very essential to actually label them properly. My outer disk corresponds to my linear function, whereas my inner disk corresponds to my parabola. So for the outer disk, I'm going to have pi, the radius is the linear function, so x squared. And for the outer, I had the parabola, so x squared, and then all squared, dx. I'm not going to complete this integral. This is really straightforward, just the product rule, but I will give you the final answer, and it should be 2 pi over 15. Okay, so I encourage you to actually finish this off and then see if that compares. We're now going to take it one step further, and this is the next two slides is sort of the hardest cases that it can be. We're going to rotate not around axes, but around specified lines. Okay, so once again, you have to draw this, otherwise it would be near impossible to set up these integrals. So we would like to rotate the same region as we had on the previous slide, but now around the axis, around the line y equals 1. Okay, so you will actually quickly notice that the picture looks very different from what we've seen before. Okay, so here are my axes, and now I draw in my lines, or my curves. So I have y equals x. Here it is. Once again, let me label it right away so I know that this is my line. And then I have my parabola. You know what? I'm going to have to scale it down a little. So this is going to be y equals x squared. Now, I know that my point of intersection happened at 1, which means that this was also 1. Actually, I might as well label them this way. And now I have to rotate this whole entire thing around y equals 1, which is, of course, this horizontal line right here. Okay, so now, again, thinking about how we rotate this, we're rotating the region bounded between these two curves around this line, right? So once again, I'm going to draw in the most opposite of looking region, which my line is going to get rotated to somewhere like here, right? And then I need my parabola that's going to get rotated something like this. Okay, and now again, you're really going to have to switch on your three-dimensional thinking and think about how it's this region rotated around this whole way. So once again, I have that bowl piece, right? And it's a hollow bowl. So when I'm drawing in my typical discs, if we're going to use discs in this case, discs usually are easier to set up, but cylinders sometimes are really worth it as well. So if I were to set up my discs here, I need my outside disc this way, and then I need my inside disc, which is going to be this guy right here. Okay. Once again, for whichever way you choose to remember it, if I'm rotating around y equals 1, it's essentially the same as rotating around the x-axis, but shifted. So if we're using disks, rotating around the x-axis or anything parallel to the x-axis would mean that my integral is going to be in terms of x. And then the other way, of course, to derive the same fact is if I were to draw in one of my disks with thickness, let's say I draw in my outer one with a thickness, my thickness is parallel to the x-axis, which means that my integral is going to be in terms of the x as a variable. Okay, and so we can use the same setup as we've used before. It's going to be an integral of pi r outer squared in terms of radius minus pi r squared for the inner radius. And here I know my variable has to be dx. I can also immediately put my limits of integration because I know that this inside of these two curves spans between 0 and 1 in terms of x. Right? So it's going to be between 0 and 1. However, in this case, thinking about the radius will require a little bit more careful analysis. Okay, so let's think of what is our outer radius and what is our inner radius for these disks. So for my outer disk, it's my red guy right here. The radius is no longer just x or y. The radius for this outer integral is, or disk, is this guy right here, right? And so this is going to be something actually quite, something that requires actually a little bit of careful analysis. Let me just erase. Oh, yeah. Okay, let me not erase. I'm just going to have to keep pointing. There's a lot of stuff already going on in this picture, right? So what I need is the radius of the outer disk, which is this much, right? Obviously, my outer disk rests on my parabola right here. So if I think about this point, maybe let me label this guy, this point right here, for some x value, this point has coordinates x and then y. The y coordinate, because it's on the parabola, is x squared, right? So this point is x and y, but I don't want this height or this width. I want this height. I encourage you to pause the video here for a second and see if you can figure out the expression for this length in terms of everything you already have on the picture. Okay, so if you've given it a little bit of thought, you would have noticed that, look, this line, y equals 1, this length is 1, and this height we can also determine from the coordinates of this point. So this little height that I've highlighted is x squared, which means that this little bit, which is the radius of our disk and the piece that we're interested in, is going to be the whole thing, which is 1, minus the thing we don't want, which is the height here, which is x squared. So the outer radius is 1 minus x squared. Similar logic will hold for the inner radius. The inner radius is going to be this guy right here. So now its point here rests on my y equals x as the curve. So if I want to label this point, it's going to have coordinates x and x because it lies on y equals x, right? And then once again, if you want to take a second here, you will recognize that this whole length is 1. This length is x because that's the y coordinate of that point. And so what I want here is the longer distance minus the shorter distance, which is 1 minus x. Okay, so then my integral turns into integral from 0 to 1. Pi outer radius, which is 1 minus x squared all squared. This square is this square. Minus pi inner radius, which is 1 minus x all squared dx. Okay, this, as I said before, and it's going to be the same for the next one, except with one additional consideration, is essentially the hardest setup that you're going to see for these integrals. When your radius is no longer just your x or your y value, but rather you're rotating around another line, which makes you take into account the fact that this line was also positioned at some distance away from your volume of revolution. Okay, for our last example here, let's take a look around rotating the exact same pieces again, but now around x equals 2. Okay, so once again, the picture is going to look quite different from what it was before. I know what a picture is going to look like already, but you might have to, when you guys are doing this on web work or in the exam, you might have to sort of scale your axes or redraw your axes a couple of times before you can really fit everything you want to fit on them. Okay, so my region is y equals x, and again, let's label this, and my parabola y equals x squared. Okay, now recall that the point of intersection is 1, and I am trying to rotate this whole thing around x equals 2. So I'm trying to rotate it around here. Okay, and I can already see that my axis here is not going to be quite long enough. Okay, so this is going to be my line of rotation. Okay, so take a second here and think about, if I'm rotating this around this line, where is it going to land? This point rotated around this line is going to land here. This point rotated around this line is going to end up here. So drawing your most extreme points, I can see that this guy is going to travel up to 4. And the common point of intersection is going to connect to here. And then I'm going to have my image of my line and the image of the parabola, or something like this. Make it a little bit thicker. Okay, and then once again, this whole thing is rotated, so I'm rotating this region around this way. So these guys are going to be connected here. Maybe let me draw some temporary connection lines, right? So it's going to be kind of like, again, a bowl, much wider and hollow, but a bowl nonetheless. Okay, so with this in mind, I'm going to erase these last lines because they're just going to crowd my picture of when I try to draw in typical discs. I'm going to again use the disc method. And again here, you can use the general formula sense to tell you that, okay, if you're rotating around x equals 2, which is parallel to the y-axis, your integral is going to be in terms of y. Okay, now let's draw in a typical disc. Here again, I know I'm not going to have the inside to it, so I know I'm going to have a washer actually, right? So I'm going to have, and again, if you want to actually draw in a disc with a thickness, you will see that the thickness here is spanning along the y-axis, which is exactly why your integral is in terms of y. I'm not going to join the thickness, not to busy my sketch. This is my outside disc, and this is going to be my inside disc. Okay, so once again, I can use the same setup as before. Pi r squared for the outer radius minus pi r squared for the inner one. And I know my integral is going to be in terms of y. I can already pause here for a second before going to the next step and see, okay, I have to be in terms of y, but my current functions are given to me in terms of x. So maybe let's do that first. So the functions are y equals x will become x equals y, so not much change there. But y equals x squared, to be rewritten in terms of y, has to be rewritten as plus or minus root of y. Here I can see that I'm only taking the positive one, so it's going to be root of y. These are going to be my two functions rewritten in terms of y. Excellent. Okay, now let's take a look at our radii. So I need to figure out what is the outer and what is the inner radius. Again, as long as you're rotating around the x and y axis, these guys are going to be just your x or your y value. The moment you start rotating around some other axis, it's not going to be that. So let's take a look at the outer one. So the outer one, my red one here, the radius of my disk is this value. If you want to take a second here, pause the video and try to figure out what does it actually have to be. I know what the coordinate of this point is. The coordinate of this point is x, and it lies on the line, so it's x. And what I want is the radius, which is this much. Okay, so if I want this much, I know that this whole thing is 2. Okay, because this was rotating around x equals 2. So this is 2. This is x, because that's the x coordinate of this point. And I want this value. So I have to subtract the smallest from the biggest. So this guy is going to be 2 minus y. Oops, sorry. So I actually should have labeled this in terms of y, of course. Right, y and y. Similarly, I'm going to go through the same analysis for the smaller disk. Okay, so I'm going to think about what is this point correspond to in terms of its, what is this point's coordinates, right? And so the x-coordinate is, now I'm going to have to be more careful. The x-coordinate is root y, and the y-coordinate is just going to be y, right? Because I'm trying to write this entire integral in terms of y. And again, now I have to think about the inner radius, so this value here. Things that I know are that this whole thing is 2, and this thing is the x-coordinate of my point, which is root y. And I want this value. So the bigger minus the smaller, I'm going to get 2 minus root y. And now I can put this whole integral together. So I have 2 outer radius, which is 2 minus y squared, minus pi inner radius, 2 minus root y squared dy. And now I got to think about my limits of integration. I go in terms of y, so I'm rotating this region. So I have to go from this point to this point. But that is, once again, from 0 to 1. Let's take a look here at one really cool application of how discs are actually used by doctors during everyday procedures. So echo is a standard ultrasound technique that takes images, two-dimensional images of slices of the heart. So slices meaning this isn't actually the entire image of the heart, of course. It's just an image of some depth of the heart, right? So a technician specifies how deep do they need to take the image taken, and then the machine produces the image of the ultrasound that is unfortunately two-dimensional, which our heart, of course, is not. So what can we derive? What kind of information can we derive from there? Now, this is actually the image of a heart of my friend Miroslav Lovric. You might recognize the last name here. This, if you remember, for chapter on discrete dynamical systems, we used a supplementary material, a different book, and Miroslav is one of its authors. So Miroslav went to have his heart examined prior to a trip to New Zealand, where he was going to be climbing some mountains where the air was thinner than everywhere else. So they needed to make sure that his heart can actually process blood with less oxygen concentration in it. So what the technician does here, if you notice, is that they actually measure something within the heart. If you notice these pluses, these are the points that the technician points out on the ultrasound, and the machine actually does the rest. Now, this technician got lucky because the machine actually did do the rest. When my daughter went for an appendix procedure earlier, the technician actually told me that they do the measurements, but for volume calculations, the technician has to do it by hand. I'm going to walk you here through what the technician would do and what the machine does for them in this particular case. So once these 3 measurements are taken, the machine actually extrapolates what the length would be. So this 5.02 centimeters is the length of somewhat centered portion within the part of the heart we care to measure the volume of. And so once you have this, you know that this is 5.02 centimeters. We're going to break up this entire distance into smaller pieces. And in this particular case, the machine approximates it with 15 little segments. Okay, so we're going to take the whole length and split it into little portions, each of the same width. Okay, so what we have here, of course, is we know the entire length. We know that we want 15 segments. So now we know the length of each segment here. This thickness here, the thickness of each of these slices, is going to be 0.335 centimeters. The machine then uses this length to actually extrapolate a whole other bunch of numbers. And I'm going to do this by hand, so my calculations might differ slightly from the machine's because its extrapolations are hidden, and I'm going to write mine out. So knowing that this is 0.335, what the machine does is actually approximate these diameters for each single slice. So what I have here, for example, is I've eyeballed that this diameter would be about 2 centimeters, this would be about 2.5, and so on all the way up. Now, in the next step, of course, we recognize that this is somewhat of a familiar setup already. All I have to do is think that this is my axis of rotation because this was drawn about halfway and with the longest length across. And then what I'm going to do is build circular discs with these as their diameters rotated around my axis. So for example, here's my first one. Now, of course, I am making a simplifying assumption that the heart will be perfectly circular at each single spot. Now, I am taking different radii for each circle, but I'm still making the assumption that the heart is a perfect circle in the cross section. That's of course not correct, but this is the best we can do with two-dimensional images trying to approximate a three-dimensional object. Okay, so once I do that, I simply continue all the way up through this axis, constructing discs of the given radius. Okay, so what ends up happening is I would like to approximate the volume of the entire part of this heart using circles like discs stacked up on top of each other. One thing to note, of course, is they all will have the same thickness but different diameter. And this is already, it should be already somewhat familiar. If you recall how we constructed the Riemann sums on 2 dimensions, we have taken the curve, any curve, right? And then wanting to approximate the volume underneath it, we simply split it into pieces of the same length. Okay, the same length, not what I have drawn here, and then constructed rectangles on top of it. This is a 3-dimensional analog of the exact same procedure. I am taking a certain length, I am splitting it into equal sized pieces, and then I'm putting a structure on top of each one. So once they're all stacked up, I can simply add them all together and get the approximate volume of this portion of the heart. So let's go through a few calculations here. I start off with knowing that the disc diameter here was 1 centimeter, which means, of course, that the radius is 1. So this portion of it is 1 centimeter. And I know that the thickness was 0.335. Remember that the thickness was the whole thing divided by 15. Now, all I need to do to figure out what is the volume of this little chunk is, in fact, so let me point to it, the volume will be simply the volume of the disk that I've just constructed. So by our formulas, it's pi times the radius squared times the thickness, 0.335. So this 0.335 is what within our integrals is known as the dx, for example, or dy. And here I have the familiar pi r squared portion. So now, if I know the diameters or radii of each one of these slices, all I have to do is calculate the volume of each slice separately and then all the way up add them together. So this is what we're going to do. The next one is going to be 1.25. The thickness is the same, so I'm still plugging it into my formula of pi r squared times the thickness, and I'm getting the next available volume of the next slice that I have. Going all the way up, we continue in this manner. And what I actually really want to do is go to the very last one. Now notice that the axis of rotation here isn't like we can do better than actually rotate around the fixed axis. And I am doing a little bit better by shifting my circles. You can see that this one is centered somewhere here, and this one is centered here, and so on. And this last one is centered a little bit ways off altogether. So doing all of this, I can calculate all the diameters from top to bottom, which means that I can half them all to get the radii. I can multiply them by pi, and then multiply by the thickness to obtain the total volume of the heart once I add them all together. Now, doing these calculations, I actually get 50.29, and my units, of course, were centimeters here, so I'm going to get centimeters cubed, and this is my approximation. If we look back at the ultrasound image here, this is what we've done. We've split this into 15 regions and calculated the volume, but the machine actually calculated the volume for us. So I got 50.29 and the machine got 50.11. Now I'm assuming that its interpolations from the known distance here to the actual radii are better than mine, but our results are pretty close together, right? So this is literally the procedure that underlies these technical machinery in the hospitals. And as I mentioned before, the technician for my daughter's appendix ultrasound said that their machines are not capable of that, so they have to go through this exact same procedure by hand. And I was incredibly impressed that she actually pulled out and said, yes, yeah, we use Riemann like some structure, but to calculate the volumes. So you go to the hospital and you're going to encounter all kinds of applications of mathematics that we're doing within this course. Good news for Miroslav is that his heart was deemed to be healthy enough for him to actually go to New Zealand and climb some mountains. This was pre-pandemic, so this was still allowed. Hopefully we will be back in those types of scenarios sometime soon.